All right, now we're going to talk about an almost example of the central limit theorem. When engaging with this, we'll see how the central limit theorem is very useful here, but we can't get asymptotic results we want maybe with the central limit theorem alone. In particular, we're going to look at estimating the variance and the standard deviation. This will be important later, as we will want to use that estimate of the variance and standard deviation. In addition, the techniques that we will talk about for analyzing this asymptotic behavior will be really important as we engage with future results. In our example, we're going to consider n IID random variables, z1 to zn, drawn from a distribution f on the real numbers. We are going to imagine that they have a variance sigma squared that is less than infinity, and we are going to let mu denote their mean. All right, we talked about employing the central limit theorem when thinking about empirical averages, in particular when thinking about the sample mean. In addition, the sample variance, when the mean is known, can be thought of as a simple empirical average. In particular, we see right here that the sample variance can be written as the empirical average of the zi minus mu squared. So if we let yi denote zi minus mu squared, then this sample variance, again with the mean known, is just the sample mean of the yi. In this case, under very mild conditions, we can use the central limit theorem and Chebyshev's inequality to say both that the sample variance minus the true variance is big OP n to the negative 1/2, and more specifically, that if we look at that difference and scale it up by square root n, we actually get convergence in distribution to a normal with mean 0 and variance that involves the fourth moment of z. We're now going to move a little bit past that and think about estimators that are not quite empirical averages of IID random variables. In particular, we'll see that we can often relate them to empirical averages of IID random variables. So let's consider actually estimating the variance in practice. Here, the population mean mu will be unknown, so what we're going to do is plug in an estimate for it, this z bar n, the sample mean. So again, if we let yi now be zi minus z bar n squared, then our estimate is really just the sample mean of the yi. However, the yi are no longer independent. So what can we do? How can we analyze the asymptotic behavior of this estimator? The first thing that we're going to do is we are going to try to remove this z bar n from this empirical average term. So we're going to do a short calculation that shows us that we can rewrite our estimator in this form. All right, so let's begin that calculation. So what we're going to do is we are going to take that representation for sigma hat squared n, right? This is 1 over n, sum I equals 1 to n. Where we had zi minus z bar n, the quantity squared, we are going to add and subtract mu, the population mean. And in fact, we are going to break this up into two terms. We're now just going to multiply this term out, and we get 1 over n, sum I equals 1 to n, of, the first term will just be zi minus mu, the quantity squared. We will also have a term mu minus z bar n, the quantity squared. And then we will have two terms that look like this piece times this piece. So plus 2 times zi minus mu times mu minus z bar n. Great. So now we can take this sum and we can break it up into three separate sums. This piece, the sum over these, and the sum over these, and we'll see that many of these will simplify. So the first term will just look like 1 over n, sum I equals 1 to n of zi minus mu, the quantity squared. The second term actually does not depend on I. So since we are averaging n identical terms, we will see that this is just equal to mu minus z bar n, the quantity squared. And for this final term, this piece depends on I, this piece does not, so it can factor out of the sum. So we will then have plus 2 mu minus z bar n times 1 over n sum of zi minus mu. All right, so this first piece we're not going to have to worry about. This second piece we're going to hold off on worrying about for now. For the moment, we are going to look at a part of this third piece. We are going to pay attention to this for one moment, and we will see 1 over n sum zi minus mu. This is actually going to be z bar n minus mu. And so that means this whole thing, we have a z bar n minus mu and a negative z bar n minus mu. So this will actually be equal to this piece in red is just going to be negative 2 times mu minus z bar n, the quantity squared. And so that means if we combine this piece and this piece, right? This is mu minus z bar n squared. This is negative 2 mu minus z bar n squared. So that's just going to give us a negative 1 mu minus z bar n squared. And so finally, then this is equal to 1 over n sum I equals 1 to n zi minus mu, the quantity squared, minus mu minus z bar n quantity squared, which matches exactly with what we have here. The beauty of this result is that we have taken our empirical average that had this annoying z bar n in it, and we now have transformed that into an empirical average of IID terms, right? Because these now have a mu in them as opposed to a z bar n, and an additional term that has our z bar n in it, but that maybe we can understand the behavior of in a more straightforward fashion. So now let's look at these two pieces and let's think a little bit more about what's going on for each of them. So we have this piece in blue that's an empirical average of IID terms. So if we think about that term, right, 1 over n sum zi minus mu, the quantity squared, we know that this minus sigma squared times square root n should converge in distribution to a normal with mean 0 and some variance. The variance is going to be the variance under f of z minus mu, the quantity squared. And additionally, we could say that this empirical average minus sigma squared is big OP 1 over square root of n. All right, now if we want to think about this second piece, this red term, well, we know if we don't square things that z bar n minus mu is big OP 1 over square root of n. Right, it converges to 0 at roughly a rate of 1 over square root of n, and we could also employ the central limit theorem here. In addition, however, because now this piece is squared, that tells us that if we square this, it basically converges to 0 at double the rate. So 1 over square root n squared becomes 1 over n. We showed results related to this before, that if you have two sequences converging to 0 and you multiply them, their rates then multiply. So rewriting what we had before, often rather than looking at sigma hat squared on the left, we take sigma hat squared minus sigma squared, and we say estimator minus truth is an empirical average of mean 0 terms plus something that converges to 0 at a rate of faster than 1 over the square root of n. And before we showed that that was big OP 1 over n, which means it is also little OP 1 over square root of n. So again, we have an empirical average of mean 0 terms, a term that converges to 0 faster than n to the negative 1/2, and this rate, n to the negative 1/2, or faster than n to the negative 1/2, is very important here. Why is that so important? Well, it's important because this term converges to 0 at exactly a rate of n to the negative 1/2. So if this term converges to 0 more quickly, that in some sense says, well, it is negligible and the asymptotic behavior should be dominated by this term, right? And here we have exactly what I said. Now, again, we want to think about either zooming in or scaling our sampling distribution if we're thinking about formally asymptotically what's happening. So in this case, we look at estimator minus truth upscaled by square root of n. And we see we now have two terms. We have this empirical average of mean zero terms scaled up by square root of n, and this term that converges to 0 in probability. Now we know by the central limit theorem that this will converge to a normal distribution with mean 0 whose variance is equal to the variance of each of these. And again, intuitively, this additional little op1 term, this additional term that converges in probability to 0, shouldn't really play a large role asymptotically, right? Because we have, again, once we scale up by square root of n, one term that stabilizes, that doesn't converge to 0 and doesn't shoot off to infinity, and another term that converges to 0 in probability. So we imagine this will play a dominant role in the asymptotic behavior of our estimator minus truth. So how do we formalize that? Well, we use a theorem called Slutsky's theorem, and here I'm only stating part of Slutsky's theorem. I'm calling this the additive part of Slutsky's theorem, and we will return to Slutsky's theorem later. And it says, imagine you have two sequences of random variables, xn and yn, and these are both sequences on the real numbers. Imagine that xn converges in distribution to some random variable x, and yn converges in probability to some constant. Then xn plus yn should converge in distribution to x plus c. In our case, we are going to be taking c to be 0, and x is going to be a mean 0 Gaussian distribution. So, applying Slutsky's theorem to what we had before, we see that a scaled version of our estimator minus truth, again, is equal to this scaled empirical average of mean 0 terms plus a term that converges to 0 in probability. This converges to a Gaussian in distribution. This converges to 0 in probability. So their sum converges to that Gaussian in distribution. Slutsky's theorem was just a nice formal way of allowing us to say, this is not important asymptotically. This also tells us that estimator minus truth is big OP n to the negative 1/2. So it converges no more slowly to 0 than at a rate of n to the negative 1/2, although we know that rate is precisely correct because of the central limit theorem, and thus also we have consistency, right? That's the weakest result, but sometimes what we're going to use, that the sample variance is consistent for the population variance. And as a reminder, this is when we didn't know the population mean, so we had to plug in the sample mean as an estimator. Just to recap that, what did we just show? We just showed that the sample variance is consistent for the population variance. In fact, the difference converges to 0 at a rate of 1 over square root of n. And further, if we scale up the difference by square root of n, then we end up with convergence and distribution to a mean 0 Gaussian. So as a final piece, we often actually care about estimating the standard deviation, not the variance. So how are we going to engage with that? Well, we have our sample variance estimator, and we could take the square root of that, and that could be what we call our sample standard deviation estimator. And again, this is only a function of the data. It doesn't involve the population mean. And we might ask, well, is this standard deviation estimate consistent for the true population standard deviation? And using what we've seen before, we can answer in the affirmative, yes, it is. So how do we do that? Well, to start, square root is a continuous function. By the continuous mapping theorem, we have that if sigma hat squared converges to sigma squared, then if we apply the continuous function square root, then sigma hat will converge to sigma in probability. We actually proved this statement, the continuous mapping theorem for convergence and probability, earlier. In addition, because square root is not only continuous, but away from 0, it actually is differentiable and has a bounded derivative, we know that the rate of convergence of sigma hat squared to sigma squared is then the same as the rate of convergence of sigma hat to sigma. And again, we showed this before as well, but because sigma hat squared minus sigma squared is big OP n to the negative 1/2, that means sigma hat n minus sigma is also big OP n to the negative 1/2. So again, that means our sample standard deviation is not only consistent, converges in probability to the true standard deviation, it also means that it converges at a rate of at least 1 over square root of n. And later we will show using the delta method that this difference suitably scaled actually has a Gaussian limit as well. So just to summarize, we did two things in this discussion. The first is that we showed our variance estimator sigma hat squared and our standard deviation estimator sigma hat are consistent for the variance and the standard deviation, and in particular that they're root n consistent, and that we will use later. In addition, we discussed this idea behind this expansion here, where we write an estimator minus truth as an empirical average of IID terms plus something that converges to 0 in probability at a rate faster than 1 over square root of n. And we will return to this in general. This representation is a very common tool that we will use for proving asymptotic normality of many different estimators.